We've looked at rocks in an environmental perspective. We looked at things about rocks, of how they weathered and how they could transmit water, so whether they are aquifers and aquicludes. And then we also, in another lab, we looked at topographic maps. And we looked at how to determine which way was downhill and which way was uphill and slopes and things like that. What we're going to do today is we're going to put those two labs together and look at groundwater processes. So here in the groundwater processes, we can then take a look at how water flows through the rocks, okay? And we can contour it. Well, some of the background. You already know what an aquifer is. Aquifer flows water. It's porous and permeable. In other words, things can move through it. Certain rocks make aquifers, soils make aquifers, and we get a lot of water movement through these areas. Okay, and you kind of have, instead of thinking about water as you know, once it gets underground, you can't see it, you don't know what it looks like. Think about it that it kind of looks like what we see on the earth with water, where water flows downhill, you know, in big sheets, and it will just percolate through the rocks underground or soils, and that's how it works in general. And in most cases, you got to worry about that porosity and permeability. Now, in addition to that, different rocks will flow water differently. Obviously, an aquiclude does not flow water. Aquifer does. But think about a limestone. Remember, we saw a limestone where you drop a little bit of acid on it and it dissolves. Okay, well, the same thing happens on a big scale. And this big scale dissolution of limestone produces what we call karst. Okay, and karst is a type of topography where you have a lot of features on this. It tends to be very flat surfaced areas. You get sinkholes in them all over, which are little craters on the surface, and underground are a bunch of caves. Okay, and a sinkhole basically is where a cave collapses, or the roof of the cave will collapse, and you make a crater above it. Okay, caves are simply like water pipes. They carry water along their underground streams where the water is moving along underground. Okay, and so that's what caves are about. So things you've seen about them with the stalactites and the stalagmites, the little icicle things hanging down. You saw the the artificial cave over in the Newark Museum. That type of stuff. That is how the caves are formed. And so what we're going to do then is by looking at that, we can look at where the groundwater goes, how it's flowing, and things like that. It makes a good illustration of what's happening underground. Okay. In addition to that, there are problems, obviously, with pollutants, with withdrawal of groundwater that will cause things to subside. And all of those things then go along with how water works underground. And so today what we're going to do then is you're going to take things that you already know about, the rocks and the contours, and we're going to make an analysis of how we can apply this to real-life problems. First exercise you're going to do is on this diagram, you will see a map. This is a topographic map. This is all about sinkholes. So what you're going to look for are little depressions on the surface. And since you are so good at doing topographic maps now from that last exercise you did, you can identify sinkholes. So what you want to do then is look around this map and find the areas that have a lot of these circled depressions with the hachard marks showing it towards the center. Those are going to be sinkholes. And then you've got to be careful with sinkholes is where you're going to build your houses and other roads and things like that. And so the questions you're going to answer on here are deal with looking at the areas that have a lot of sinkholes and then determining where and why you would be careful with your building. Second exercise you're going to do, have a topographic map of an area down in Florida, a place you probably all go for spring break. And down here you'll see again a bunch of sinkholes. But the difference is these sinkholes are full of water. Now the thing is that this water that you see in these sinkholes makes a little round pond. And on the top of the water you will see it has an elevation. It's in blue. Okay, now if we contour the water in an area, groundwater levels, you can figure out which way is downhill for the water and you'll understand which way is flowing. So what we're going to do is there's two pages that you look at. First one is where we see the basic topographic map that shows the surface contours, and it also has all these little sinkholes in it, all of the industry that goes around, the houses, everything else. Now, turn to page 207, and there is a blank map, shows all of the lakes on it, a couple of them with the heights on it, the rest of them without. What you need to do is to go back to the first page, transfer all of the heights of water that you see onto the heights on the second map. Okay, so you will have a bunch of lakes in there, all of which will have numbers on them. And these will be your data points. So what you're going to do then is you get a regular old contour map, except this time it's not a contour map on the surface. It's a contour map on the water table. Okay, so you will wind up with a contour map that's subsurface, it's underground, and it shows the height of the water table. Now, what can we do with that? Well, if we take a look at with a contour map, you will wind up with a bunch of lines with different heights. Okay, so suppose this one is 100 feet, 80 feet, 60 feet. Okay, here then we are going downhill. Okay, higher levels 100 feet, lower to 60 feet. Now what you have then in here is we can tell which way the water is flowing. Water always goes downhill. And in fact, it goes perpendicular to your contour lines. So if you draw in an arrow perpendicular to the contour lines, you can predict which way the water is flowing. So for example, if I had a, some waste up in here, perhaps a landfill or something like that, and it was leaking, we would know that the leakage would head basically in that direction. If you lived over here, you probably wouldn't be affected by it, okay, unless it's strange conditions. So therefore, understanding how to say which way the water flows is a very important thing, okay, and so that's what you're going to do in this part. Now, in addition to that, we have some data that goes along with the flow, because they did a little test. They threw some dye into the water and see which way it goes. And so by looking at how far that dye went, which way it went, and how long it took for the dye to get from one sinkhole to the next, we can predict the speed at which the water flows as well. Okay, and so therefore those are the types of questions that you are going to have in the book, and you'll get a series of them. You don't have to do all the questions from the book, but you'll be given a handout that tells you which ones you need to answer. Well, now in our next survey of different kind of groundwater situations, we can talk about artesian wells. Now an artesian well, you've learned about in class, this is when you have confining aquicludes around an aquifer. So basically this aquifer is being sealed in by tight confining beds that will let it so that none of the water can leak out. And so what happens then is this area turns into kind of like a garden hose, okay, where you have a high water pressure stuck inside of this plastic hose. Now what happens is that if you drill wells that don't reach this pressurized confined layer, then they just flow like normal wells. You have to pump out the water. However, if you take a well and penetrate into that confining layer, it's like poking a hole into your garden hose. What happens? The water comes squirting out. Okay, so an artesian well basically is once you penetrate that artesian layer, that confined layer, that pressurized, the water comes squirting out in the air. Okay, and so some places you might have seen pictures where actually the wells will gush water, and that's what happens in an artesian system. So the next exercise is to look at artesian systems, and we have kind of little ones here in New Jersey in a couple of places, but out west they got some real big ones. So what you'll do here is just look at them and answer a couple of questions based on artesian systems. So with this artesian system, then what are you going to do with it? Well, in the book you will notice in this figure you will see that there is two sets of contours that overlap each other. What you have is a surface topography, and as well you will have a water pressure surface. Now what you look for is to see where you get intersection between the water table surface, the water pressure surface, and the topography. Where you get those will be a line between water wells, if you drill a well on one side, where the water table is above the topography, water pressure surface, then the water will flow naturally out of the wells. If it's below the topography, in other words below surface, it won't flow naturally. So what you're going to do on this exercise is you're going to find the places where the two intersect. So where you get a contour, a blue contour and a brown contour that have the same exact value. Where that is, you put a dot, okay, and that goes all around, and it can hit several times. So don't just, once you find it once, quit. Look at any place, the contour lines, where they overlap each other and you get the same numbers, put dots in. And then what you're going to do is connect up the dots, and then you will define an area, one side of which will be where water flows naturally from wells. The other side will be where water does not flow naturally. So all you have to do is see where is the water pressure surface above the topography, then it flows. If it's below, it doesn't. Last one we have is if you withdraw water from the ground, what it will do is it will pull water out of the ground. Okay, so normally you have a certain amount of water in the ground, okay, and it keeps the ground filled up. Think of this like a sponge, okay? Think about what happens to a sponge. You get the sponge wet, and it sits there at a certain size. Now let it sit out for a few days. What happens to it? It dries out, and you notice that the sponge gets smaller. So when you withdraw water from certain rock types, certain soil types, they will tend to shrink. So what we get is land subsidence around certain areas where you're pumping a lot of water out of the ground. And so you can get quite impressive land subsidence in certain places by doing that. So what we're going to look at now is another hazard of groundwater, in that when you pump wells, it withdraws the water. You get what's called a cone of depression around the well where the water is being pulled out, and we can have land sinking. Okay, and so this exercise is to look at a place in California where they have a lot of land subsidence because of withdrawal of water. So what you're going to look at then is you're going to look at the map to see where the areas are experiencing the most subsidence. Then we're going to look at some historical tables, and we're going to calculate how fast the subsidence is going. I mean, that's an important thing, especially when you live close to the ocean. Get too much subsidence there, and you get ocean water coming in on you. That's not too good. Anyway, so that's one of the things you can look at. In addition, we're going to look at what's called a hydrograph. And a hydrograph is the measure of how high the water is at a given time. We have a graph of wells in California where you can see the differences in height with time. And clearly they've been pumping a lot of water out of the ground to irrigate their fields and use as drinking water, and so they're suffering the effects of that. That's why it's so important to conserve water, certainly in there, because their ground surface is sinking. They have to be very careful. And so your next set of exercises is to analyze an area which is undergoing ground subsidence because of the withdrawal of water. And that's what these exercises are for.